Okay, so in the first video, we talked about limits as x approached infinity. Now we're going to talk about the limit as x approaches any real number. Okay, so first check out the difference in the notation. Limit as x approaches c of our function. Okay, graphically, what we look for, the limit exists if and only if the limit as x approaches c from the right-hand side of the function is equal to the limit as x approaches c from the left-hand side of the function. So not only do those things have to be equal, but they're going to be some number L, and that'll force the limit as x approaches c to be that same value. So these things are called one-sided limits. All right, so the limits from each side of c have to approach the same number in order for the limit to exist. So let's look at the graph. So in order to investigate the limit as x approaches 1, so we have a lot going on at x is equal to 1. The limit as x approaches 1 from the right-hand side. Okay, so here's where x is equal to 1. So if you just sort of need to dot that in. If I'm on the right-hand side, that would mean numbers bigger than 1. So I'm going to look, and this is going to take practice. Okay, as you do it here, I think you're going to be like, oh yeah, this makes sense, but it's going to take some time. So the limit as x approaches 1 from the right. What I need you to do, what I need you to understand is that you're just focusing on 1. So as I get closer and closer to 1 on the right-hand side of it, this is the graph that I focus on. No other part of what's graphed on this piecewise. So as I get closer and closer to x is equal to 1, what are my y values approaching there? My y values are approaching 2. So it all comes back to the fact that these limits are approach statements, and the limit itself is a y value. Okay, so now let's look at y from the left-hand side. Not y, excuse me, 1 from the left-hand side. Okay, so that would be the graph on literally the left-hand side of the line x is equal to 1. So I'm just going to focus on the portion of the graph that's right by the line. And then you have to say to yourself, okay, as I get closer and closer to this, what are my y values approaching? Well, now my y values will be approaching 5. Now notice here on both of these they're open circles. So the function doesn't exist there, but the limits are approaching these y values. So that's why the limit can still exist. So now, does the limit as x approaches 1 of my function? It does not exist. And the reason for that, what justifies it, is the fact that the limit from the right-hand side of the function is not the same number as the limit as x approaches 1 from the left-hand side of the function. Now, if I ask you the question, what is f of 1? So now when x is equal to 1, what's my corresponding y value? That would be 3. And why is it 3? Because that's where the closed circle is. And that's what the closed circles represent graphically. They represent y values at corresponding x values. So we'll do more practice with graphs. But I need you to focus on and understand what it means to be from the right and the left. And notice that I didn't even discuss every other part of the graph. I just looked at the portion of the graph that's right at the x value that I'm approaching. All right, so now algebraically, we always start with direct substitution, and you'll see what I mean in a minute. So the limit as x approaches c is either going to give us a number that we call L. When we do direct substitution, that substitution is going to look like 0 over 0. Or lastly, when we do direct substitution, that substitution is going to look like number over 0. And each substitution tells us something different. All right, so limit as x approaches 5, every single thing starts with direct substitution. So wherever I see x, I'm just going to replace that with the number 5, because that's what x is approaching. Okay, so this would give me a limit of 13. So if the limit as x approaches c, I start with direct substitution. When I plug that number in, I get an output, so 13 is just simply my limit. Number 18, wherever I see an x, Again, I'm going to replace it with the number 5. Okay, and where does the number 5 come from? That's what x is approaching, right? So these are not meant to trick you, okay? You literally take the number that x is approaching. So I get 13 over 10. So 13/10 is just simply my limit. Now number 19, so wherever I see an x, I'm going to replace it with 3. Okay, so I get the square root of 4 all over 8. So 2/8 reduces to 1/4. So 1/4 is the limit. 13/10 for number 18 and 13 for number 17. Now, one mistake that students have made in the past, they look at this and they tell me that they want to put a plus or minus there. Plus or minus is only used when you're solving a quadratic and you have to introduce the square root. So if I ask you to solve that, that's where plus or minus 2 comes from. When the square root is already in the expression, the answer is just what we call the principal root, which is the positive root. So don't be putting the plus or minus in there. We're not solving here. All right, example 20. Everything starts with direct substitution. Into the numerator, I get 0. Into the denominator, I get 0. Okay, so a couple things here. So let's go back. So the limit as x approaches c. I plug the number in, I get 0 over 0. Okay, first of all, that would tell me that f of c does not exist. There's no corresponding y value, because when I plugged it into the function, it gave me an answer that is not a real number. All right, algebraically though, 2 things you're going to look for. You're either going to multiply, nope, let me change that. You're either going to factor or multiply by the conjugate. And we'll talk about this one in a minute. Okay, so when I look at this, this is definitely factorable. The numerator is factorable. So I'm going to rewrite my limit statement because I haven't done anything with it. My numerator, hopefully you recognize that as the difference of perfect squares. X plus 2 times x minus 2. Still have my x minus 2 on the bottom. Now notice you get something to cancel. Okay, so limit as x approaches 2. So what we've just done is we've simplified our rational expression, rational function here, x squared minus 4 over x minus 2, into this simple linear function. So now that I've simplified it, I can go back and I can make a direct substitution. And once you make the direct substitution, you no longer need the limit statement. So I replace x with 2, therefore my limit is 4. Okay. So to recap, that f of 2 does not exist. The limit as x approaches 2, however, does exist. That's a number. That's what we just found to be 4. In class, we'll talk about putting those 2 things together. All right. Always start with direct substitution. So my numerator, I get 1 minus 1. So again, I get 0 over 0. So now here, this expression does not lend itself to be factored. Notice that there's a square root in there. And we've done a lot of rationalizing denominators. Okay, we simply started with something like 3 over the square root of 3. And when we do that, we multiply by square root of 3 on the top and bottom, and it gets rid of that radical. Remember when we were dealing with imaginary numbers and complex numbers, although this is not, we multiplied by the conjugate here. Whatever we do to the numerator, we have to do to the denominator. And I'm going to do it out here because I don't want to do it with the longer problem. So I'm multiplying binomials here. First, outer, that should be the minus, outer, inner, and then last. Remember, we chose the conjugate because it gets the outer and the inner to always cancel each other out. So when we look at an expression like this one that now has a square root and underneath the square root is a variable, we're still using the exact same method. Okay, so I'm going to do the algebra steps behind it. So I have 1 minus square root of 1 plus x. This is my original, all over x. Now when I pick the conjugate, I'm only going to change this minus sign to a plus sign. Everything else stays the same. Whatever I multiply the numerator by, I have to multiply the denominator by the same. Okay? So first things first, in the denominator, I do not want you to distribute. You just be making more work for yourself, and I'll explain why in a minute. Now in the numerator, I want you to recognize that you don't have to FOIL the whole thing. The outer and the inner cancel, so I'm just going to multiply the first and the last. So 1 times 1 gives me 1. A negative times a positive, it'll always be a minus sign. Now I'm going to put this in red. The square root of anything times itself, the square roots cancel, and I'm just left with what's underneath. I'll say it here. We'll do it together in class. Please put a binomial in a set of parentheses. And the reason that that is so important is because I then have to distribute that negative to both terms. If you don't distribute the negative, it's going to make your answer the opposite of what it should be. Okay, so the whole deal is attempting to simplify the original. If I think about going back and making a direct substitution again, I'm still getting 0 over 0 at this step. Okay, so it doesn't do me any good. So let's continue. So the 1 minus 1 cancels, and I get negative x all over x times 1 plus. All right. Direct substitution, I still have 0 over 0, but now look what happens. The x from the numerator will cancel with the x from the denominator. So once you've made that simplification, once you get something to cancel, now I'm going to reintroduce my limit statement. And my simplified function will now be negative 1 over 1 plus square root of 1 plus x. Okay, now when I put 0 back into the original, into the simplified function, I get 1 plus square root of 1 is 1, so my limit would be negative 1/2. So it seems like quite a bit of work, but the thing that I have to get you to understand is you have to cancel something in order to get the limit to exist. So let me go back here. There's something I want to add. This 0 over 0, this is known as indeterminate form. So think about what indeterminate means. You cannot determine the limit in the form that the original is written. So algebraically, we have to do something to simplify it. Okay, so let me just finish up these last 2 examples, and then we'll talk about the rest in class. Every limit starts with direct substitution. So this one gives me 1 over 0. Well, what's different from 0 over 0, which is indeterminate? 1 over 0 does not exist. So the limit, it just simply does not exist. When I plug in 1 here, I get direct substitution gives me 7 over 0, so my limit does not exist. Okay, so to go back to this slide, and I do recap everything together. When direct substitution gives you number over 0, 2 things. F of c does not exist, okay, because when I plugged that number in, it didn't give me a real output. And furthermore, the limit as x approaches c just doesn't exist. There's nothing more algebraically that you can do. It does tell us something graphically, but we'll talk about that in class. All right, so that'll do it for 19.1's videos.